Okay, the law that we want to look at here is the law that relates, that we use to calculate the force on a moving charge due to a magnetic field. Now, we haven't really talked about magnetic fields, so we're just going to say that B is a magnetic field, and it has units of newtons per amp meter, and we'll see why, and we'll see how magnetic fields arise just a little later. But right now, let's just accept that there is a certain magnetic field and a given charge with a given velocity. At least charge and velocity are vector quantities, obviously. A charge, velocity, and magnetic field are vector quantities, as is the force that results. There's also another version of this law where you multiply current times distance increment, displacement increment, and that's what you would use if you have a charge flowing through a wire, or a charge somehow flowing through space or through some other medium. And IDL takes the place of QV, and there's a very simple reason for that correspondence that we're not going to talk about just yet. This is just another form of the law, and IDL is I times the vector dl is equivalent to Q times the vector V. Now this is the one we're going to use for the present. Okay, so now in the first problem we have a situation that you should have already thought about and sketched, where the velocity is in the positive x direction, the magnetic field in the positive z direction. Okay, so the velocity is 3 times 10 to the 6 meters per second. The charge being negative 1.6 times 10 to the negative 19th coulombs, QV is going to be in the opposite direction because Q is negative. When you multiply a vector by a negative quantity, you get a vector in the opposite direction. So QV is in the negative x direction. Now, what we want to do is QV cross V. V is this way, QV is this way. Fingers in the direction of the QV vector, curl toward the V vector, and we get a vector force in the positive y direction, in the direction of the j vector. Now, we see that the force is going to be in the direction of the j vector. We don't need to do any more to calculate that, although that does come out of the calculation that we do up here. Okay, so the magnetic field in this case is 0.02 newtons per amp meter. And we'll talk more about this unit. This unit is also called a Tesla. It's a SI unit, but let's just work with newtons per amp meter right now because it's a little more direct. Okay, so what's the magnitude of our vector? What's the magnitude of our force vector? So we could say that our force, and again without the arrow over it, this just means the magnitude of the force, is the magnitude of QV cross B, which is the magnitude of QVB sine theta, because that's where sine theta is the angle between V and B. Okay, now what is that? Well, first of all, what's Q? And it took me a long time to drag this out of people in class, but wanted to kind of get some kind of interaction going. Okay, well, Q is, as given, 1.6 times 10 to the negative 19th coulombs, and actually that's not Q. Q is negative, but we're doing a magnitude here, so we're just going to take the magnitude of each quantity. The velocity is 3 times 10 to the 6 meters per second, and V is 0.02 newtons per amp meter. And theta, well, what's the angle between the QV and the B vector? Okay, well, this one is in the direction of the negative x-axis. This is in the direction of the z-axis. So that angle is clearly 90 degrees. Not sure why I didn't get much of a reply when I asked about that, but and the sine of 90 degrees is 1, so this just becomes 1. So all we have to do is multiply these three quantities, and we can do that rather easily, and I believe that comes out 9.6 times 10 to the negative 15th newtons. Why newtons? Well, we have coulombs here and we have seconds here. So we have a coulomb per second, which is an amp, and it's going to be divided by this amp. And that leaves us, of course, with a meter in the numerator, which we divide by a meter in the denominator, and leaves us units of newton. So that's a very straightforward calculation. Now, What's the direction of F? Well, we just found it by wiggling our right hand appropriately. We could also do this in terms of unit vectors. Okay, the direction of F is the direction of QI cross K, and Q being negative, this is going to be in the direction of negative I, and so we have a negative times our I cross K. Our I cross K vector is negative J, and the negative of that, of course, is J, so that we do get a force in the J direction. We could also calculate QV cross B using determinants. I didn't have room to write in my units up here. My units would be Coulomb meters per second, which would be amp meters, so that when multiplied by this, we get newtons. And we see that, well, we have J times this times this. It's going to have, well, it'll be negative J times this if we follow the rule for determinants, so that we get negative J times negative 9.6 times 10 to the negative 15th newtons, which gives us positive 9.6 times 10 to the negative 15th newtons times J, and the direction is the direction of the J vector. The magnitude is the same as the magnitude we calculated here, so we confirm our conclusion that the force has this magnitude and that it is in the direction of the J vector.